let's move on to the paths. So what we want to do is make another table. The path from A to B, from B to C, and from C back to A. And then I also like to put a column at the bottom where we total these up. Total for the cycle. And what are we interested in? We're interested in the work done. That's the work done by the gas in our system, by our system. And Q, that's the amount of heat added to or removed from the system. And the change in internal energy, delta U. And there's a couple of things that we know and we like to use. We like to use Q is delta U plus W. And because this is an ideal gas, that means that delta U is N times CV times delta T. And let me just work that out real quickly. Delta U, N, CV, delta T. I need a little more room. I'll rewrite it here. CV we can write as R over gamma minus 1. R we know, 8.314. Gamma in this case is 1.67. And so I'm left with N times 12.41 times delta T. So this is going to be a really handy way to calculate delta U when I don't have other information. Gamma, 1.67. You kind of have to look that up and know what it is. It depends on the molecule, right? How many degrees of freedom it has. How many ways can you add energy to that molecule? If it's a monatomic molecule like this was, then you can't add energy in very many ways. You add energy, the molecule starts moving faster translationally, right? It moves faster. But a molecule like oxygen, that's O2, that's diatomic, it can not only move faster, but it can also vibrate because it has a connection, right? Two molecules can vibrate. A water molecule has even more degrees of freedom. It can spin, it can vibrate, and it can translate. It can move, it can vibrate or spin. So you can add energy in a lot of different ways. And that's what gamma depends on. So in this case, it's 1.67. All right. So let's start filling in what we know and working through here. So let's look at the path from A to B first. And the first thing we know is that W is 0 because the volume does not change. Right? If the volume doesn't change, the gas can't do any work. We can't do any work on it. So those are linked together. The work done is 0. So that tells us that Q is equal to the change in internal energy. And what are we going to do? Oh, we're going to use this formula we just got for delta U. Delta U is N times 12.41 times delta T. And we've got 2 moles of gas. And delta T is going to be 600 Kelvin minus 200. And what do I get? 9,928 joules. Okay, so that's a positive number. You have to be careful here. We're delta T is always final minus initial. So it's the temperature at B minus the temperature at A. And we get a positive value. So the gas, for both Q and delta U, we get positive values. So we have to put energy into the system. We have to add heat to the system. That's what a positive Q means. And its energy goes up, right? We put that heat in, and those molecules are moving faster. They have more internal energy than they had before. So it's delta U is positive. Okay, let's look at the next part of our path, going from B to C. And here, the temperature does not change. And if we have an ideal gas, then the only thing the internal energy depends on is the temperature. So that tells us that delta U is going to be 0, which means that Q is equal to W. And because we are on an isothermal path, we can use the work done is nRT times the natural log of the final volume over the initial volume. Two moles, 8.314 joules per mole Kelvin. 600 Kelvin is the temperature, and we've got the natural log of 0.0998 over 0.0333. That's the natural log of 3, and I get 10,960 joules. Again, I got a positive value for the work done because the gas is expanding. The gas is doing work on the environment.